Alright, welcome to Chapter 12 video. We're going to go over some practice problems that we didn't get to in class. I'm just going to pick stuff at random out of the book. It may or may not be on your homework, and do some examples. So, flip the page. Practice problems convert Kelvin to Celsius. You should do that if you have the formula, no problem. Keep flipping, keep flipping. Alright, here we go. First problem. Problem number 3 in the textbook says, when you turn on the hot water to wash dishes, the water pipes have to heat up. How much heat is absorbed by a copper water pipe with a mass of 2.3 kilograms when its temperature is raised from 20 degrees to 80 degrees Celsius? So you're looking at how much heat is absorbed when the temperature changes. So we notice that temperature change is the indicator for thermal energy. So we know right away we're going to be looking at E therm. So I could put delta E therm. Delta because it's going to be changing, or it's going to be absorbing energy because the temperature went up. Formula is m times c times delta T. Remember that the delta T, since it's a change in temperature, can be either Kelvin or Celsius. So we went from 20 degrees Celsius up to 80 degrees Celsius. So my delta T is 60 degrees Celsius. My mass of water is given to me in the problem, 2.3 kilograms. And the last thing I need to do is my specific heat. My wife is laughing at me. What are you laughing at, Trace? Okay. The specific heat. It doesn't give us a value in the problem for specific heat. However, it tells us it's a copper pipe. So in your textbook on page 318, there's a table of specific heats. And if you glance over here, specific heat, you look up copper, and it says this is 385 joules per kilogram Kelvin. And that's for copper, yeah? So you take out a calculator, you multiply 2.3 times 385 times 60. Kilograms cancel with kilograms. Here, the degrees Celsius cancel with Kelvin because the size of 1 Kelvin and the size of 1 degree Celsius are the same. So even though they're different units, the increment that they have is the same. They cancel. And so your answer is going to come out in joules. And that's going to be the amount of energy that was absorbed. I don't have a calculator, so that's as much as I will do. But again, something is changing temperature. That's the indicator for thermal energy. The formula is mc delta T. C is the specific heat, which you can get from the table if it tells you what material your object is made from. Okay, keep scanning. Problem 4 and 5 are pretty similar. Keep scanning. Okay, problem 6. A 200-gram sample of water at 80 degrees Celsius is mixed with a 200 grams of water at 10 degrees Celsius. Assume there is no heat lost in the surroundings. What is the final temperature of the mixture? So we start, draw a little picture. We start with 200 grams of water, and this temperature is 80 degrees. And this is water. And we're adding it to 200 grams of water, which is 10 degrees Celsius. And this is again water. So what's going to happen, because this one is hotter and this one is colder, the heat is going to transfer this way, from the hotter object into the colder object. And it specifically says in the problem, assume there is no heat lost in the surroundings. So however much energy, thermal energy this guy loses has to equal the amount of thermal energy this guy gains. So I can set up delta E therm number 1 equals negative delta E therm number 2. The reason there's a negative sign is because one of them is gaining it, the other one is losing it. So the opposite sign there. For E therm 1, I can put in M1, which is 200, C1, which is the specific heat of water, times delta T. Remember, is always final minus initial. So nope. That's bad. That should be a T. T final minus. Instead of T initial, I can put 80. Oh, man, I'm messing up a lot. Sorry. So this is T final minus 80. On this side, I can put negative. Mass is 200. Specific heat is the specific heat of water. And here I got T final minus 10. Okay. Because this is mc delta T. And this is mc delta T. This is very common that you're going to have when you have heat transfer between two objects at different temperatures. You'll do mc delta T of the first one equals mc delta T of the second one, because whatever energy one of them lost has to equal the amount of energy the other one gained. This minus sign in the front again is because the temperature is one of them is going up, one of them is going down. So the numerical value is equal, but one will be positive, the other will be negative. So the minus sign fixes that. We're going to solve this equation for T final. Notice that CW, specific heat of water, is the same in both sides. That will cancel out. And in fact, since the mass is exactly the same for both of them, in this case the mass will also cancel out. And it becomes a very simple problem. Yeah, I would distribute this minus sign here, and we get minus TF plus 10 equals TF minus 80. Okay, if we add TF to both sides, I get 2 TF on this side. If I add 80 to both sides, I get 90. Add 80 over here to the 10, you get 90. And you get that TF equals 45 degrees Celsius. Now, this one was kind of easy because it was the same material on both cases, so the specific heat canceled, and it was the same mass on both sides, so the mass canceled. That's probably not going to happen that often. So that's why I showed the full setup of mass of the first one, specific heat of the first one, and then change in temperature of the first one, and likewise for the second one, because normally those things will not always cancel out. In this one, you might have just used common sense and said, hey, equal quantities of the same material, the temperature at the end is going to be right in the middle, the average of the two, and you can see the average of the 80 and the 10 initial temperatures gives us the 45 we had at the end. So you might have seen that right away, but if you show all your work, it'll help build a pattern of being able to do it even if the quantities are not the same mass or not the same material. Okay, let's do one more example from this section. Section review, let's take a look here. Converting units, temperature, thermal energy. Number 12 is a concept question. Here, I'll just write this down so you know which one we're doing. Number 12. Could the thermal energy of a bowl of hot water equal that of a bowl of cold water? Explain your answer. Well, if they ask a question about E thermal, even though it's a concept question, the first thing I would do is write down my formula. E therm equals mc delta T. Okay, we're comparing hot water and cold water. So the material is the same in both cases, yeah? So the C value is the same in both cases. So the C value can't really matter because it's the same in both cases. So could we get the same E therm from two different things? Well, they say in one of them the temperature is real hot and the other one it's real cold. Well, if the temperature goes up, then the mass should go down. So if you had a small quantity of hot water or a large quantity of cold water, they might actually contain the same total amount of thermal energy. If that doesn't make sense, maybe ask in class, but hopefully it does make sense. Remember, the thermal energy is, it's a very much kind of like potential energy of gravity. A small object held up really, really high, or a really big object held up just a little bit off the ground. They could have the same amount of potential energy, because one is higher but smaller, and this one is hotter but smaller, or colder but larger. So same idea there. Thermal energy, heat flow. One thing you should know is that water has a very high specific heat. We had mentioned the number. The specific heat of water is 4180 joules per kilogram Kelvin. If you look at the table on page 318, you'll see it's much, much higher than almost all other materials. So things that have a high water content don't change temperature very often. This is something, for example, when you have a city built near the coast, the temperature is usually moderated and it doesn't have high temperature swings between the day and the night, or even between winter and summer, because you have a giant body of water that can absorb or give up a lot of thermal energy without actually changing temperature very much. And so likewise, there's a question about a baked potato on your dinner plate, and I encourage you to think about the fact that potatoes are mostly water when you're answering that question. Let's choose one more math question. Critical thinking. Let's zoom ahead a little bit to the end. Mastering problems. Coffee cup, problem 54. Okay, this will be our last one for the video. A 400 gram coffee cup is 20 degrees at room temperature. It's then plunged into a hot dishwasher at a temperature of 80 degrees. If the temperature of the cup reaches that of the dishwasher, how much heat does the cup absorb? Assume the mass of the dishwater is large enough that its temperature does not change. So we start with a 400 gram cup that's at 20 degrees Celsius. So a dirty cup sitting on your sink, and we put it into a big pool of water that is 80 degrees Celsius. Okay, and this is water. And this is water. Actually, oh, no, it's not water, sorry. It's glass. Our coffee cup is glass. So the first thing we need to do is go look up the specific heat of glass. So we flip over in our textbook to page 318, and we look up glass, and we see its specific heat is 840 joules per kilogram Kelvin. 840 joules per kilogram Kelvin. Okay, and the question asks us, when we put the cup into the dishwater, the temperature of the cup reaches that of the temperature of the dishwater. So the T initial for our cup is 20. What is T final? T final, it goes all the way up to 80. And normally you might think, okay, if the cup is gaining energy from the dishwater, shouldn't the dishwater cool down? And it would, but they're telling us the quantity of dishwater is so high that the amount the temperature decreases by is negligible. You know, it might go down to 79.99 or something, but we're just going to ignore that. So we're looking at the T initial as 20 and T final as 80. And the question is, how much thermal energy did the cup absorb? So this one is actually kind of easy because we have our formula. So MC delta T. We know the mass of the cup is 400, which we should put as 0.4 kilograms. Specific heat, we just looked that up in the table on page, 318. So that's 840. And the change in temperature, if we went from 20 up to 80, that's a change of 60. If you check your units here, you've got kilograms. Here it's joules per kilogram Kelvin. And here again, this is, it's degrees Celsius. Degrees Celsius, but remember Kelvins cancel with Celsius because they're the same size. Kilograms cancel kilograms, leaving us with just joules. So we multiply these numbers together, 0.4 times 840 times 60, and whatever you get, that's the amount of energy that was absorbed by this coffee cup. And you could also, a lot of questions they might ask, or I'll ask on a quiz, how long does a certain process take? Time, yeah? So once you've figured out how much energy it takes, remember that power equals energy, the change in energy or flow of energy over time. So therefore time equals the total amount of energy divided by the power. Power is the rate at which it's delivered. So you might have a microwave, say you're heating something up in the microwave, and it's a 1,000-watt microwave. That means it's delivering 1,000 joules per second. Or your stove flames might be delivering, 300 joules per second. So if you figure out the total amount of energy, and you know the power source that's providing the energy, you can figure out how long it takes to heat something up or cool something down. And that's another common question or extension on what you've been doing. So sorry I wasn't being able to do this in class, but hopefully these 3 examples can kind of help elucidate the formulas, comparing the energy of one object and another object getting transferred back and forth, and how to use specific heat properly. Make sure you look up those values on page 318. All right, good luck. See you in class.